In section 4.2, we look at exponential functions. And this should be a review topic for many of you, but we will go ahead and treat it like it's brand new. So here's an example. Suppose we start with one bacterium, and the bacterium splits into 2 bacteria every hour. That means the population is doubled every hour. So let P of t donate the population of bacteria after t hours. This table below models the population growth. So in the beginning at t equals 0, we have 1 bacterium. After 1 hour, we have 2. After 2 hours, we have 4. After 3 hours, there will be 8, right? So each time we're just doubling the number. And you can see that after a few hours, it really starts to grow rapidly. This function can be modeled by the function P of t equals 2 to the t power, because these numbers here are just powers of 2. And you can see that's been outlined here. So, for example, 8 is 2 to the 3rd power, 16 is 2 to the 4th power, 32 is 2 to the 5th power, etc. So the function P of t equals 2 to the t models this growth. And this type of function is called an exponential function. Let's go ahead and get a formal definition. An exponential function is a function of the form f of x equals some constant c multiplied by another constant a raised to the x power. So an exponential function has a variable in the exponent. The domain of this function is all real numbers, and the range will vary depending on the values of c and a. Now, one thing about these constants is the constant a must be a positive number. So we are only going to be raising positive numbers to powers, but the number c could be positive or negative. The number a is an important number, and it's called the base of the exponential function. So now what we would like to do is just evaluate some exponential expressions using a calculator. So in the first one here, we have 0.5 raised to the 1/3 power. What we want to do is approximate this using a calculator. Now, all calculators are different. They have different keys for raising a number to a power, so I won't show it here, but I will do this on my calculator and import the picture of what that looks like. So you'll notice on my calculator, when I plug this in, it looks exactly like the expression that we've been given. So we have 0.5 raised to the 1/3 power, and we get this number. Now, if we round this to 4 decimal places, we are going to cut this number off after 4 decimal places, which you can see here. And this 0 here does not round that number up. So this is approximately equal to 0.7937. Now let's go ahead and evaluate the next 2 expressions. I'll bring those in as well. And on my calculator, they're going to look exactly like what you see here. And so rounding 2.8 to the 2.5 power to the nearest 4 decimal places, we end up getting approximately 13.1188. And rounding 4 to the square root of 2 power, you'll see that when we round this one, it's a little bit more interesting. This 9 here is going to round this 9 up, but we can't round 9 up, so we have to think of this as 29, and that 29 gets rounded up to 30. So this is approximately equal to 7.1030 to 4 decimal places. So the point is that you can raise any positive number to any power, and you can use a calculator to approximate the result. So you should pause this video and get your calculator and make sure that you're able to get these same values. Next, let's take a look at the graph of an exponential function. The simplest possible exponential function that we can think about is the function f of x equals 2 to the power x. So choosing a base equal to 2 gives us the simplest exponential function. If you plug in some various values for x into this function, you can see the approximations for those values here. So for example, 2 to the negative 5 is the same as 1 divided by 2 to the 5th power. And if you do this on a calculator, you get approximately 0.03. This is a very small number, right? It's very close to 0. If you plug in negative 2, you end up getting 0.25, a little bit larger than the last number. Plugging in negative 1 gives us 0.5. Remember that anything raised to the 0 power is 1, and then from there it's pretty simple. If you graph these points, you can see that the point negative 5, 0.03125 is this point here, and it appears that it's on the x-axis. It's actually not on the x-axis. There is some space between the x-axis and the function at that point. But it's very, very close to the x-axis because this number is very close to 0. So you can see that what is happening to the graph of this as x approaches positive or negative infinity. As x approaches positive infinity, the function is growing very, very rapidly. And so the function is also going to infinity as x goes to infinity. However, on the other side, as x goes to negative infinity, so as x is moving in this direction, you can see the function is coming down and getting closer and closer to the x-axis. And the way we can describe that is the y values there are approaching 0. Now, let me bring in a different graph so we can see this a little bit more clearly. So here is a better picture of the graph. And you can see as x moves in this direction, the graph of the function is coming down and getting very, very close to the x-axis. But I want you to notice that it never touches. So even there at negative 5, you can notice that the function is just slightly above the x-axis. And that's actually true no matter how large of a negative number we plug into the function. So again, we say that the function 2 to the x is approaching 0 as x moves towards negative infinity, and the function 2 to the x is approaching infinity as x goes to positive infinity. And again, that's a little bit easier to see because clearly as x gets bigger in this direction, the function is just getting extraordinarily large, right? So this is how we can describe the end behavior of this exponential function. So now we'll generalize some properties of exponential functions. So if we're given some exponential function c times a to the x, and let's assume for a minute here that c is a positive number, the function will look like one of the following, either this graph or this graph. So if a is greater than 1, so the number here, the base, if it's greater than 1 and c is a positive number, then we will have the graph that we just looked at on the previous page. So the function will approach infinity as x approaches infinity, and the function will approach 0 as x approaches negative infinity. You'll notice that the domain is the set of all real numbers, and the range is only positive numbers, right? Because the graph only touches positive values of y. It does not touch any negative values of y. Now, the other situation is that the base a here could be a number in between 0 and 1, like 1/2 or something like that. Now, if c is still a positive constant, then the behavior of the graph basically just flips over the y-axis. So instead of having an ever-increasing function like this, you will have a decreasing function like this. And we can see that as x goes to infinity, now the function is going to 0. And as x goes to negative infinity, the function is getting larger and larger. The domain of the function is still all real numbers, And the range of the functions is still the numbers from 0 to infinity because, once again, we don't get any negative y values. Now, if by chance the number c is a negative number, and that's not talked about here at all, but all that's going to do if c is negative is it's going to flip the graph over the x-axis. And so now your graph would be down here, or in this case, your graph would be down here. And that will affect the range, but it doesn't affect really much of anything else. So here's an example graphing the function f of x equals 5 times 1/3 to the x power. So here is our constant c, which is 5. Notice that that is positive. And our base is 1/3, so that is a number in between 0 and 1. You can also express this as 5 times 3 to the negative x power. And over here we have a table of values, and you can get these values by plugging these numbers into the function and using a calculator to approximate the result. So for example, when you plug in x equals -5, you get 5 times 1/3 to the negative 5 power. And if you plug that into a calculator, you get 1,215. So if you do that for all of these numbers, you'll see these y values. Now, if you plot those points on a graph, what you'll notice is indeed the function is coming down in this direction. And we can see that the function is approaching 0 as x goes to infinity. And we can also see that the function is approaching infinity as x moves in the negative direction, right? So that is the end behavior of this function. Now, what is the range? Well, the range is going to be all y values from 0 to infinity, but not including 0. So the range will be from 0 to infinity like this. Next, we want to graph the function h of x equals negative, and then we have 2 to the 2x. So you have to be careful here because it's easy to get your constant c and your constant a confused. So let's just think about what this really is. So we have negative, and then the number 2 is raised to the 2x. What's important here is the negative is not raised to this power, only the 2. So using properties of exponents, you can actually express this as negative and then 2 to the 2 to the x. Because what we would do when we have an exponent to an exponent is we would multiply these together, and 2 times x would be 2x. However, if we write it like this, we can see that 2 squared is 4, and we can re-express this as negative 4 to the x. And we don't actually need parentheses here at all because, again, the power here only applies to this, does not apply to the negative. So I want you to think of this as basically being like -1 times 4 to the x. So this is our value of c, and this is our value of a. And of course, I'm referring to, c times a to the x. So you'll see here that your value of c is negative for the first time, and that's going to have an effect on the graph. And the value of a is 4. So now let's go ahead and plug in some values into this function and sketch a graph. Okay, so here is a table with some values here. So if you have a minute, you should take these values of x. You should plug them into this function to make sure that you get the same values. If you plot those points on an x and y coordinate system, you'll notice that, as I mentioned on the previous page, that the graph is coming down like this, right? So what's happening to the graph as x goes to infinity and as x goes to negative infinity? Well, as x goes to infinity, we're moving this way, we can see that the graph is going down to very large values. And so we're going to say that the function h of x is approaching negative infinity. And then as x goes to negative infinity, that means on the x-axis, x is moving in this direction. We can see very clearly that the function is getting closer and closer to the x-axis, which is where the function is equal to 0. So the function is going to 0 as x goes to negative infinity. And the range, right? The range is the set of all the y values that you get. Well, in this case, the range is all the values from negative infinity up to 0, because this graph only covers negative values of y, does not cover any positive values of y. The other thing they ask us to find is the y-intercept. Well, the y-intercept is this point here, and that occurs when x equals 0. And you can see that when x equals 0, y equals -1. So the y-intercept is the point 0, -1. And the other thing they ask us to find is the domain. Well, for exponential functions, the domain is always all real numbers. So minus infinity to infinity. So again, having a graph of an exponential function really helps you determine all of its behavior, because we can see what is happening. And to get a graph, you really kind of need to have a calculator, because it's very difficult to get numbers like these without a calculator. In the next example, we want to use the graph of f of x equals 3 to the x to sketch the graph of these two functions. G of x equals 3 to the x minus 2, and h of x equals 3 to the x minus 1. So the graph here, the pink graph here, is the function 3 to the x. It's a standard exponential function. So to graph 3 to the x minus 2, we just need to remember that when you plug x minus 2 in for x, that is going to shift the graph 2 units to the right. And that's exactly what has happened here. So the graph of 3 to the x minus 2, we're simply taking every point on 3 to the x and we're shifting it 2 units to the right. Shifting it 2 units to the right. And if you do that for every single point, you will get this graph here. Now, can you make a table of values for this and points and all that stuff? Well, of course you can. But the real point here is to understand what the x minus 2 does to the original graph. For part B, we have 3 to the x and then minus 1. And we should remember that when you subtract 1 from a function, this is going to move it 1 unit down. So again, if we have our original graph, 3 to the x, which looks like this graph here, all we're doing is taking every point on that graph and shifting it down 1 unit, right? Down 1 unit. Now, one important thing to note here is that, normally the function 3 to the x, as you move to negative infinity, would approach the x-axis, right? So you can see this pink graph here is getting close to the x-axis. Well, when you shift everything down 1 unit, now it's no longer getting close to the x-axis. It's getting closer to the line y equals -1. So that does have an effect on the range, and it does have an effect on the end behavior of the graph as we move in this direction. But again, once you have a picture of the graph, all of that is much easier to understand. So next we want to talk about the number e and the natural exponential function. So the number e is this number that you see here, 2.71828182884, etc. At first it appears that it repeats, but it actually does not repeat. So it's very much like the number pi in that regard. And if you want to approximate the number e, we usually say e is approximately equal to 2.72. Now, where does this number come from? Well, it comes from the expression 1 plus 1 over x to the x power, but as you plug in larger and larger values for x. So if you take a look at this expression, 1 plus 1 over x to the x power, I've created a table of values for you to notice what this expression behaves like as you plug in bigger and bigger numbers for x. So for example, if you plug in 10, this expression will be 1 plus 1/10 to the 10th power. If you do that on a calculator, you will get 2.59374246. That's this number right here. If you plug in 100 into this expression, you get 1 plus 1 over 100 to the 100 power. And this will give you the number 2.7048138.3. And that's this number. Well, if you keep plugging larger and larger values of x in here, such as 1,000, 10,000, 100,000, or 1,000,000, what you'll start to notice is that it appears that the number is approaching something, right? Like these numbers aren't just getting bigger and bigger and bigger. They are getting closer to something. And you can see right here, if you were to round that number to 5 decimal places, that would be 2.71828. And that should look familiar because that is actually the first 5 decimal places of E. So this number E is a really strange number. It's basically equal to this expression, but as you plug in really large values for x, such as 1,000,000,000 or 1,000,000,000,000 or even more. Okay, so this number E comes from what we call a limiting process. And if you want, I can just show you kind of like where this is headed. So E is technically, we say, the limit as x goes to infinity of the expression 1 plus 1 over x to the x power. Okay, now you don't have to worry about this notation. This is something that we learn in calculus, but this is basically just saying if you take this expression and you plug in larger and larger values of x, that is going to give you this number that we call E. And it turns out that E is a really important number, as you'll see in the coming examples. So first, let's just make sure that we have a fundamental understanding of how to evaluate expressions involving E. So to do this, you'll need to find the number E on your calculator. Now, I will tell you on most calculators, there will be a button that will look like this. It will have an LN and an X, and this stands for the natural log. And then right above that button, you should see E to the X. Now, this is how most calculators will do it, but not all calculators are the same, so it might be in a different location. But this E to the X button basically just tells you when you use this function, you are going to raise the number E to whatever power you type in. So if I want to do E to the 1/3 power, I have to hit this key, right? To get the function above, we have to use this shift key on our calculator. And then I'll hit this key, and then I'll type in the number 1/3. So I'll go ahead and do this for all 3 of these, and I'll bring a photo in of each one just to kind of show you what that looks like on my calculator. And so here are each of these expressions on my calculator. We want to round these to 4 decimal places, so we're going to cut off each one of these at 4 decimal places, as you see here. And if we round these in the first one, we get E to the 1/3 is approximately 1.3956. And the next one, E to the 2.5, is approximately 12.1825. And E to the -2 is approximately 0.1353. And you'll notice on the calculator that they don't have the 0 in front of the decimal. You don't have to put the 0 here, but most textbooks will, and so that's why I included it here. So you should just take a minute to make sure that you're able to type these expressions into your calculator. So before we move on with the exponential function f of x equals e to the x, I just wanted to show you the graph of that function when compared to y equals 2 to the x and also y equals 3 to the x. So all 3 of these functions are graphed here, and what you should notice is that they all behave very much in the same way. So the function y equals 2 to the x is this graph here, and you'll see that it is increasing. You'll notice that it passes through the point 0, 1, and it gets larger and larger as you plug in larger values of x. 3 to the x behaves in exactly the same way. That's the green graph here. And that graph is coming up like this, also passes through the point 0, 1, and also gets larger and larger and larger as x gets larger. And the function e to the x is right in between those two functions. It's kind of hard to see here, but if I zoom in, you will see indeed e to the x is in between 2 to the x and also 3 to the x. And it stays in between those two functions the whole time. Also passes through the point 0, 1, and it grows larger and larger as x gets larger. Now, why does e to the x behave in this way? Why is it in between these two graphs? Well, because remember, the number e is the number 2.72 approximately. So the number e is a number in between 2 and 3. So we would expect this graph to be in between 2 to the x and 3 to the x. The domain of the exponential function, e to the x, is all real numbers. The range is from 0 to infinity. And again, it has normal exponential behavior. E to the x goes to infinity as x goes to infinity. And e to the x goes to 0 as x goes to negative infinity. Now, the thing I want to mention here is that this exponential function, f of x equals e to the x, is usually referred to as the exponential function, right? So we're no longer just talking about an exponential function. It is the most important one. So for that reason, a lot of times it is referred to as the exponential function. Now in the next graph, they ask us to make a table of values to sketch the graph of g of x equals e to the x plus 3. So we talked about this earlier. Basically, what this does is it takes the graph of e to the x and it shifts the graph up 3 units. Now you can make a table of values like they did here. You can verify these values, but basically instead of the exponential function coming down and approaching 0 as x goes to negative infinity, it's now going to approach this line y equals 3 because the entire graph has been shifted up 3 units. Okay, so the important thing here is to remember that when you add 3 to a function, it just shifts the graph up 3 units. Now let's talk about a couple of applications for exponential functions. The first is compound interest. So if you take an amount of money, let's say $P, and you invest it into an account that pays an interest rate R, and the interest rate is compounded n times per year, then after T years, the amount of money in the account will be according to this formula here. So again, P is the amount of money you are putting into the bank. So a lot of times P is called the principal. R is the interest rate, but we need to remember that this is an annual interest rate. N is the number of times it's compounded per year. So some banks will compound interest every month. Some banks will compound it every 3 months. Some will do it every day, etc. And T is the total amount of time that you leave the money in the bank, and this time is in years. And this formula will tell you how much money will be in that bank account after a certain number of years have gone by. Now, if you talk about continuously compounded interest, the difference between these two is that now the money is growing all the time, every second, every split second. So you're still investing P dollars, it's still paying an interest rate of R, but there's no longer a number of compoundings per year, okay? It's compounded continuously. And after T years, the amount in the account will be this formula. So notice that the number E is used here. So this is P times E to the R times T, whereas in the first formula, we do not use the number E. It is simply P times the quantity, 1 plus R divided by N, to the power N times T. So we have an example down here that compares these two methods to show you, what the difference would be. So let's go ahead and take a look at this one. It says, suppose $2,500 is invested into a savings account. Find the following quantities. The amount in the account after 4 years, if the interest rate is 5.5% and it's compounded monthly. All right, so for part A here, we have a principal balance of $2,500. That's P. We are leaving it in the bank for 4 years, so T is equal to 4. The interest rate is 5.5%. Now, we do need to change this to a decimal, so we need to write that as 0.055. And it is compounded monthly, so N is equal to 12, right? Because that's 12 times per year. The formula is A equals P times 1 plus R divided by N to the N times T power. This is 2,500 times 1 plus 0.055 divided by 12 raised to the power 12 times 4. And we can plug this into a calculator to get the answer. And you can see from the picture below here that the amount of money in the account here will be $3,113.63. Now, what do we get if it's compounded continuously? Well, the amount of money we are putting in is the same. It's $2,500. We are leaving it in the bank for the same amount of time. T equals 4 years. And the interest rate is still the same. It's 0.055, but now we don't have a value of N. The formula is A equals P times E to the RT. This is 2,500 times E to the 0.055 times 4. And if we plug this into a calculator, you can see that if we round this to 2 decimal places, because it's money, we get an approximate amount of $3,115.19. So, do you get more money if the money is compounded continuously? Yes, you do. Is it significantly more money? Well, I don't think so, right? I mean, this is 4 years, and how much more money do we get? It looks like less than $2 more. So what's the point of this? Well, the point is that when you're putting money into a bank and it's compounding, and you're compounding in a certain number of times per year, you can often get a reasonable approximation to the amount that's going to be in that account by just using this simpler formula. So that's the takeaway here. Now, as you're doing your homework, make sure you pay attention because they're going to want you to give precise values for these things. In our final example, it says a Honda Civic depreciates at a rate of 8% per year. This means that each year it will lose 8% of the value it had in the previous year. If the Honda Civic was purchased at $20,000, make a table of its value over the first 5 years after purchase. Find a function that gives its value t years after purchase and sketch its graph. Okay, so we need to think about how much it is worth when you bought it, 1 year later, 2 years later, 3 years later, etc. So let's bring in some variables here. So we are going to compare time versus value. So when time is 0, that's when the car was first purchased and it was worth $20,000. Now it loses 8% of the value that it had. So after 1 year, it's going to lose 8% of this value. Now the key is that if it loses 8%, this means that it retains 92% of its value, right? Because 100 minus 8 is 92. So after 1 year, the value is going to be $20,000 multiplied by 0.92. And this will give us a quantity that we'll fill in just a minute. Now let's think about how much will it be worth after the second year. Well, after the second year, it's going to lose 8% again. So at the end of the first year, this is how much it is worth. And now it's going to retain 92% of this value. So we have to take the $20,000 that has been multiplied by 0.92, and we have to multiply it by 0.92 again. After the third year, we're going to take that value, so 20,000 times 0.92 times 0.92, And we have to multiply that by 0.92 again because, again, it only retains 92% of its value. So I hope that you see what is happening here. After 1 year, we're multiplying by 0.92 to the 1. After 2 years, we're multiplying the $20,000 by 0.92 to the 2. After 3 years, we're multiplying $20,000 times 0.92 to the 3. So we kind of get the idea that after 4 years, we'll be multiplying by 0.92 to the 4th power. And after 5 years, we'll be multiplying by 0.92 to the 5th power. So what is its value going to be after t years? Well, the value v of t will be $20,000 multiplied by 0.92 to the t power. So I'll go ahead and bring in a table of values for all these to show you what it's worth at each of these years, and then we'll sketch its graph. So on my graphing calculator here, you can see I put in the function 20,000 times 0.92 raised to the variable power. On the calculator, they use x instead of t, but that's okay. And you can see that when it was new, it was worth $20,000. After 1 year, it's worth $18,400. After 2 years, $16,928. After 3 years, $15,573.76. After 4 years, $14,327.86. And after 5 years, $13,181.63. And here's a graph of that function. So when I say that function, I'm referring to this function right here. And you can see on the graph at time equals 0, it's worth $20,000. And every year it depreciates. It goes down. And you can see it's kind of leveling off a little bit more. Okay, but you can use this graph to approximate values. So you can see that, for example, after 10 years, it's worth a little bit less than $10,000, for example, right? So you can use this graph to get some approximate values for that. So exponential functions are extremely useful. They occur a whole lot in the real world, and we should make sure that we understand how to use them and apply them to real-world examples.